just took out OpenCV and we have these images and analyze them. Okay, so if this circle is here and this square is here, then this component is present, so it passes, and otherwise it's not. But the challenge there is, let's say you have a new product, and as Prodrive, we manufacture thousands of different products from huge cabinets to tiny sensors. So if we have to inspect a new type of product, it means starting at square one again and defining a new algorithm, defining your camera setup. So that's challenge one. You need skilled computer vision people to build these new inspections. And the other one is that the lighting conditions can change a lot. Environmental variations that can hinder your algorithm. Say, okay, you expect it to be a square, but at some point you move the setup and the lighting is a bit different and the square is no longer recognized in your algorithm. So we found out, we need to improve this. The vision is nice, but a really dedicated, stable application, it will work very well and you can get it running very quickly. But we need to find a way to remove the need of, let's say, people like me, computer vision engineers, because we need to scale more and we need to find a way to be more robust for environmental changes. And that's basically how we got into deep learning.
In this episode, we talked to Thomas, who works at a company called Prodrive Technologies. We explore how the company started with the AI platform and what it meant for the company to go from simple proof of concepts of applying machine learning or deep learning techniques to actually adding business value, and the journey that Thomas and his team had to take to understand and reveal all the common gotches around implementing MLOps. If you're interested in understanding the tools, the challenges, the story, the motivation, the obstacles that Prodrive has overcome in the recent few years in this journey, this episode will be exceptionally interesting for you.
Welcome to Inspiring Computing. This podcast is where computing meets the real world. This podcast aims to trigger your curiosity by talking to proficient and advanced users of MATLAB, Python, and Julia, who use these tools to deepen their understanding of the world by simulating it, exploring trade-offs, and gaining insights that help their companies add more value. In addition to proficient users, we will be also talking to product marketing, toolbox authors, package developers, and library maintainers to see what drives the development and what issues they're solving for others to benefit from. Welcome to Inspiring Computing. Great to have you, Thomas.
Yes, I'm happy to be here. Thank you for inviting me.
And you and I, we met at a PyData conference here in the Eindhoven region, and we got talking about what you do at Prodrive and how you use AI. But before we get into exactly what Prodrive is and what you do at your company, can you maybe share a few words of who you are and how did you actually get into programming / artificial intelligence in the first place?
Yeah, and actually started really with software, as I'm a bit biased to that. His father is also a technical person, so to say. He studied electrical engineering. Like me, I also studied electrical engineering after that. So I was already seeing, okay, what is interesting for me? And when I grew up, he had a lot of computers. So I was already more into computer hardware, a bit of software, sometimes a bit of programming, actually more into gaming. So really the applied part of the software, so to say. But I always found it very interesting to see what happened and to get everything working, building your own PCs, adding the latest GPU to it, and then seeing it get everything to work. And well, nowadays people might think it's really a lot more plug and play. I also grew up in the time of the IRQs and all those kind of things, figure everything manually to get it to work. And that's basically how I got into that. And then when I finished my high school, I went to the University of Eindhoven University of Technology, and I started electrical engineering. And it was really a bit doubtful, should I do electrical engineering or should I do computer science? Because I like both. And my motivation then was really, okay, so I can do computer science because I like software a lot. I like programming and all the things around it. I also like electrical engineering. And my reasoning was that if I do software now, so computer science now, it's harder to go back to the hardware side than to do the other way around, because in electrical engineering, you also get some programming. So I get a lot of C there. And computer science, they mostly are, let's say, more abstract, like Java. They teach that a lot. So my reasoning was I can better go via electrical engineering than via computer science. And I'm still here as a software architect anyway. So,
but just from understanding, so was that reasoning already when you were 18? Did you already have a good understanding of the difference of the two educational routes, or what? Because usually what happens as an 18-year-old, you're like, yeah, I don't really know what it means to be an electrical engineer and all the variations that entails. And the same also for computer science, right? There's front end, back end, goodness knows what. It's not such a clear-cut decision. In my experience, most 18-year-olds have difficulties making that assessment. But how did you figure that out? Was it with your father or friends?
So I visited some universities when at the end of high school. So I also went to Delft to see what they were offering. And I already knew Eindhoven because that's also where I grew up. So I was at high school in Eindhoven. And yeah, for instance, I actually went to applied mathematics in Delft with a friend, so a fellow student at high school. And we went there, and it was a nice thing that we found out, because for him, it was too applied, too technical.
Yeah.
For me, it was too theoretical. And you might say, how is that possible? Because actually, he really didn't like the applied part. He was really more a theoretical position. So he also went to do physics. Like physics. So physics at a different university. For me, this applied mathematics was too abstract for me. I wanted to do something that actually could do something like software or electronics, or that was basically how I found out, okay, and this is basically the route I want to take. And I knew that doing such electroengineering, in my opinion, is a really good basis, because you learn a lot. You learn about electronics, about hardware, about all kind of things like antenna, signal processing, but also software. As I mentioned, you learn C and C++, so that's really the core of programming, in my opinion. You learn about assembly. I even had a course, I remember I had to program in assembly, and there was once and never again, because I know now why we have higher level programming languages and compilers, because it doesn't make sense to do it at that low level, in my opinion. But yeah, that's basically how I got there.
So maybe just for those who are not electrical engineers, can you describe some of the options during your course that you took as an electrical engineer?
Yeah, definitely. It's a very broad program. I'd say it's 3 years bachelor's and 2 years master's, if you do everything in one go. Now, when I started in 2007, there was virtually nobody who did that in the 5 years that was listed for it. We had quite an active generation in 2007. And I think there was one person who finished his bachelor's in 3 years. And then I think a bit over 2 years did his master's. But most people on average take 7 or 8 years. So it's 2 to 3 years and more than you would expect, because it was so many things you had to learn, very broad. Especially the first years, you get a lot of math. And as I mentioned, you get the basic electronics, you get all kind of signal processing courses about your Fourier transforms and Laplace transforms for control theory. So it's really broad. And then basically in the master, specialize more towards a direction. And it could be electromechanics or antenna design. I mentioned signal processing. That's also the direction I went more into. But also, let's say, analog electronics or embedded systems, so more the digital side of electronics, to power electronics, also an important direction. So there are many things. And even what I didn't mention, optical. They have 2 big optical groups, optical communication and photonic integration, so optical chips.
Yeah.
There's really a broad spectrum where you can go. And a lot of friends ended up in different directions, but we still meet regularly. So it's really nice to see where they ended up.
Right. So there's often the kind of informal joke amongst electrical engineers is like, people say, well, you can't fix the electronics of your house. And then you try to go down this rabbit hole and say, I studied all this other stuff, and most people don't quite realize it. So I'm glad you explained that.
Yeah.
So then as an electrical engineer through trade, you then said you focused on signal processing and you did a bit of programming, but I didn't hear the word AI. So I'm guessing you didn't learn any AI as an electrical engineer?
Yes, actually, there was more during the end of my master's, I would say. Although I remember I also had a course about neural networks at the end of my bachelor's. There was a minor, they could have some electives, and there was a course about neural networks, and they had this crazy simulation package where you could have neurons and you could talk to each other. And this was pre-convolutional neural networks and those kind of things.
Yeah.
I think it just started. I think this was around, when was it? 2010 or 11. That was that course. And then in my master's, I went to the signal processing group, and they have a subgroup, let us say, called video coding and architectures. That group really started around, let's say, JPEG and MPEG. So really the coding of images and video. And they moved more towards analytics of images and video, because JPEG and MPEG is really common now. So in that sense, they had to innovate. So they were more into the analysis of images and video. And so to say, that also comes more in the domain of AI.
Yeah.
And in my graduation assignments, I worked on a system for automated road marking detection. It was actually not at Prodrive, it was at Cyclomedia, a different company. And there I did my internship or graduation assignments on this topic, where I had to recognize road markings from panoramic images. We have these cars driving around taking pictures, similar to what our big search machine company does, right? This company does it, but then sells them directly to governments and local municipalities to inspect their environments. And the goal here was to detect all these markings and build a map out of it. You actually get top-down view, so you project all the detected markings on an actual map, and you can see where your markings are. And maybe see if they're missing after a year or if they're damaged, all those kind of things you can.
Yeah.
And this is really the first thing where I applied AI in a big course or in my thesis. Mind you, this was not deep learning yet. This was the advent of deep learning. This was around 2015.
Yeah.
It wasn't really a commodity yet, although it was applied more and more in places, but you need a lot of compute and those kind of things, which are now more ubiquitous, I'd say. So that was just more traditional support vector machine done on certain image points and key points in the image to recognize the markings. Basically how it started.
This was, what language were you using, if I may ask? Is it C, MATLAB, Python?
It was in MATLAB.
Okay, very good. And then, but this I think leads itself to what you're currently doing now at Prodrive, right? So now you work at a company called Prodrive Technologies?
Yes.
But can you maybe give us a bit of context? What is actually Prodrive Technologies and what do you actually do there?
We worked there for, I think, let's see, almost 8 years. So I started in 2015, right after I graduated. And so Prodrive Technologies is an electronics company. They were founded in 93. So actually 30 years ago. We'll have a big party this year to celebrate that. And it was just original founders. They started, there's the two of them, I think even on the Eindhoven University of Technology, and on a company to manufacture, let's say, electronics. And I think back then even was power electronics. And yeah, fast forward to what they have now. Now it's a company of over 2,400 FTE, so full-time equivalent. And just to compare, when I started in 2015, it was around 600. So in about 8 years, it has quadrupled. And now it's not only power electronics, they have many different industries and many different markets, so to say, that they have customers in, of which the major ones are, for instance, automotive, a lot of medical customers, and semiconductor. So I think those are the main ones. And yeah, but what does Prodrive then do, right? So we manufacture electronics. What does that mean? To give you some example of some products that we make. So for instance, one is a gradient amplifier, but that's basically the thing that powers your MRI scan. So you have a big MRI scanner in an hospital, and there's all these big fields, magnetic field being generated that need a lot of power. And basically we build the electronics to provide that power to that machine. So that's our electronics application.
So that's power electronics, right? So not everyone knows the term. So power electronics, high voltage, lots amount of power, all the electronics to make sure that things don't blow up when in use and to keep it safe.
So high voltages, high currents, and high currents mean high temperature, you need cooling. So that's the big things we have also in our test facilities where we have huge, let's say, fake MRI machines where we actually can test our electronics. So that's still a very big part of the Prodrive. But as I mentioned, we do much more now. So we also make linear actuator systems. So we have a big program at Prodrive where we make linear motors. So you can basically imagine this as, for instance, a big application where we have an elevator shaft and the elevator doesn't move up and down with a cable. It moves up and down with a linear actuator. So people might know this from a roller coaster. You have these roller coasters that launch you basically instead of inclining you somewhere up a hill and then going down. You have roller coasters that launch you. This is actually similar, but actually not horizontal, it's vertical. So basically is an elevator shaft where you just keep on going. And we basically built the propulsion system. So the linear actuators plus the control, the software, electronics. So again, there's some overlap, but also we also built these magnetic motors. So linear actuator uses permanent magnets in this case. So we have a whole facility to glue these magnets to the backplate, so to say.
So just wanted to say, so what you do is you actually get the magnets itself and you do the assembly. It's not that you're buying the motors themselves and then integrating it. When you say you're manufacturing and making it, you're really going to the almost rawest component possible, right?
Yes. I think that's what differentiates Prodrive a bit, because that other companies might outsource certain parts, but we indeed try to do much in-house as possible. Basically almost avoiding outsourcing, but obviously we really can't, and we're at capacity, we need to do that. But our basic motivation for that is that we want to keep this competence in-house. And that really allows us to use this competence for products that are similar or processes that are similar. So I think that's the main motivation for it. And basically you mentioned it, we glue these magnets in-house. That's one of our processes. We have many of these processes in-house, and I can give you a few examples. So we have a machining department. So basically raw aluminum or steel comes in a block and we mill some fixture out of it or some mechanical part that is used for a customer. Let's say in the plate where you glue the magnet. And this is, again, an automated facility. So you can automatically run these machines overnight and they can prepare these mechanical parts for you. And if you make electronics, you have to pick and place electronics, and it's called actually PCBA assembly. So printed circuit board assembly, PCBA assembly, where we have lines of these machines that automatically pick and place all these tiny components on those boards, including inspection if they are placed correctly and testing to see if it actually works after everything has been assembled. So you see you have the mechanical part, you have the electronics part. That night they put them separately, but you need to put them together. So we also do final assembly. And for some products, actually high volume products, we have fully automated assembly lines. And basically what happens there, all the components come in and every step in the process, for instance, a robotic arm that picks up a component and places it in the final product. And then it moves to the next step. And then another robot places another part. And this actually is fully automated, including the logistics and the testing. Yeah, it's maybe hard to imagine what that would look like, but we have some opportunities sometimes to have tours at Prodrive. So in that sense, you can actually witness it. And it's really amazing because you expect people to walk around and do things. You don't need to. The thing runs by itself as long as it's fed with components. And I mentioned the automated logistics. So that's another thing we do.
Yeah.
This automated production line, automated manufacturing. Then we have automated logistics where we make these AGVs, or I think so it's an automated guided vehicle. But I think the more common term now is an AMR. So it's an autonomous mobile robot, which we have manufactured in-house to supply our manufacturing solutions from automated warehouses with components. So these things drive around autonomously, stand in front of it, it goes around you. So it is also safe to work together with them. And I mentioned testing, because then all these products that come out, they have to be tested and validated that they actually work, which in our case is also just a smaller line. And these AGVs can bring components that are ready and manufactured to the testing line, validate them there. And it's not only testing, it's also calibration. It is pressure test if it has to be airtight. And then there's these final functional tests. And then basically it could be packed into a box.
Okay, so let me see if I get this straight. So this company that you work for, Prodrive Technologies, it started off with power electronics. And then you said, okay, power electronics, we need to design our sensors, our own boards, our own mechanical things. And then as time progressed, you started building out your own solutions, so you didn't have to outsource them. But as you build them out, you then also enabled yourself to sell these things to others, right? So you have your own assembly lines, your own robotics. You've solved a whole bunch of pick and place problems that you could sell to others, but the driving force was you to make your own products quicker, better, and have more control. Where I think most companies who go down that route, if I understand correctly, they kind of have a big bag of money and then they get system integrators and they buy components from different companies, and then it all comes together, and then they're building something, but they didn't really control every single component. And you are different because you're controlling everything and building it all. And as time progresses, you go lower and lower from the mechanical building, the electronics, the software, the sensors, the integration, the testing. So I like what Prodrive does, but then I have to ask, how does AI and computing come into play here? And how does it affect your job?
I didn't explain what I then do at Prodrive, right? I started there in 2000. After graduating, I worked on some automatic visual inspection algorithms. Fun thing, I also did an internship before there. So Prodrive already knew me, and that's why they knew, hey, this guy, he does some nice things, we should hire him. So I did basically an application for automated inspection of sealants, let's say glue. Puts a certain glue on the product tape to see if the glue is in the correct place. So I was really continuing on more different types of automated inspection applications. And so I then already saw this is nice, but we also need a nice robotic automation framework. There was already a project that started on that. And this is basically the software framework that automates and controls all the manufacturing machine, the assembly machine. So let's say you have an automated robot, you have a camera, and you have a conveyor. There's one piece of software that talks to all of that and basically controls it on a system level. And the algorithms were integrated in that piece of software. So that's basically our own piece of software that we used to call Prodrive Robotic Solutions, and now actually call Prodrive Work Center Automation, because it's gotten way more generic than just automating robots. It automates much, much more. And a lot of those algorithms were integrated into that. And that was C#. It's still a C#. You have to deal with finding the right library to do that. And okay, that's all nice. So I did that for a couple of years, built some nice manufacturing lines. The manufacturing line I just mentioned to you is also a project that I did before I'm in the role of what I do now. And we found out, okay, we do all these inspections, and we have to use these, let's say, dedicated computer vision algorithms, because that's what we used back then. So we just took out OpenCV, and we have these images and then analyze them. Okay, so if this circle is here and this square is here, then this component is present, so it's pass, and otherwise it's not. But the challenge there is, and well, actually there are multiple challenges. Let's say you have a new product And as Prodrive, we manufacture thousands of different products from, let's say, huge cabinets to tiny sensors, or maybe even, let's say, the size of your phone to 2-meter high cabinet. Those are basically the range of products that we make. So if we have to inspect a new type of product, it means starting at square one again and defining a new algorithm, defining your camera setup. But that's challenge one. You need, let's say, skilled computer vision people to add all these new inspections. And another one is that the lighting conditions can change a lot. So environmental variations that can hinder your algorithm. Say, okay, you expect it to be a square, but at some point they move the setup and the lighting is a bit different and the square is no longer recognized, and your algorithm fails and people lose trust and they start doing it manually again, which also has all kind of downsides. So we found out, we need to improve this. Computer vision is nice. If you have a really dedicated, stable application, it will work very well and you can get it running very quickly. But we need to find a way to remove the need of, let's say, people like me, computer vision engineers, because we need to scale more and we need to find a way to be more robust for environmental changes somehow. And that's basically how we got into deep learning.
Okay. So before we go into the deep learning part, I want to double click there on something. You said, how do we remove people like myself, right? So that's an interesting statement, because most people are scared of losing their job, but you're working your way out of a job or changing what you do so that you can scale. And if I understood correctly, what makes it different in your particular case is you have the same physical space where you're producing two or multiple types of components which are very different shape and feel. And the goal was to be able to say, okay, this week we're going to build little components like this and make sure it works, but we want to have as quick as possible turnaround that the following week we build something bigger, different, customized, whatever. And then the question is, how do I check this without having expensive computer engineers take a couple of months to create an algorithm that does this right? And can I do this overnight? Yes or no? And that's where you go into the deep learning. Is that kind of the idea?
Yeah, exactly. It really depends on, let's say, component availability. If we can make our products, especially in the last few years, it was really problematic, right? To get the right products and components. So for us, it was really, see, which product can we make now? And now we probably can make this one. So we need all the inspections up for that one. And then also customer demand suddenly goes up for another product and goes down for another. So you really have to be able to deal with this. As I mentioned, we have thousands of different products, a lot of different customers. We don't only build our electronics. No, we make many different products. So that's also the challenge we have to.
Because I guess what many companies might be saying, let's hire or outsource this to as cheap as possible labor and have as many eyes on it. It's just quicker and easier to have people looking at this instead of having deep learning models look at it. So then you wanted to do it the different way and saying you want to control it. So is this where you are responsible for creating and maintaining and putting these models into production?
Yes. You need to mention that you could also let people do this, right? But you have to mention that we do most of our manufacturing, bulk of our work in the Netherlands. So letting people do this is also not that cheap. Although we do have a lot of products that are very, let's say, high-end electronics. So these are it's not just, let's say, a simple LED. No, it's a really complex component that is very expensive, and it's mostly business to business. And you also need to mention what people might not know, Prodrive Technologies. Our customers are mostly other big tech companies in our vicinity. We do a lot of business to business, so to say. So we make really important components for other, maybe more well-known companies in the vicinity of Eindhoven. And why would deep learning actually help here, right? How would that solve it? How I see deep learning is, so maybe I should explain that first, right? Everybody knows the term AI, and the term AI, in my opinion, says completely nothing. It's literally artificial intelligence. And you could even argue that if you write a really simple piece of software that just looked at a variable and says, if this variable is larger than 10, I return true. And if it's smaller than 10 or equal to 10, right, I return false. You could argue this is artificial intelligence because that's rule-based artificial intelligence. So in that sense, any piece of software could be regarded as artificial intelligence. So I find that term quite vague. Everybody uses it for everything, but what people mostly actually are going towards, they mention AI, is more machine learning. And what that means is you have a certain piece of software, you can call it a model, which you actually train on data. So that's very abstract, but we obviously did it on a lot of image data. So that's probably the examples I keep on using. Let's say you have images of a product, or maybe even simpler, of a component on a product, and you have images of that component where it's present and where it's not present. So then you have this data set where you have labels, data set and labels, and then you have your model, And what basically you do during training, you provide the model with the images, and the model tries to basically guess what the label is. So during training, you get feedback, right? So there's one round of training, and then you say, yeah, you did these, you did correctly, and these you did incorrectly. So then it knows, okay, so apparently I have to tweak myself a bit. That's the interesting part that it can do by itself, by basically back propagation. And I won't go into that detail. I think that's quite so basically the model can learn by itself how to find the relation between the input data and the output labels. So input data would be an image of a component either present or not, and the label would be yes, it is present, or no, it's not present. Power then, what it can do, it can generalize. So you give it another image it has never seen before, and then it can basically already infer what the label should be. Hey, is this component present in this new image that you have never seen before? And that's basically machine learning. So you train a model with data to be able to predict on unseen samples. But then what's deep learning? So I mentioned machine learning. Deep learning is basically, let's say, a subclass of machine learning where this model is built from inspiration of the human brain. It's basically an artificial neural network where you have all kinds of neurons that are connected through layers, many layers. So deep means many layers, and that are connected. And basically your information flows through. And in the end, you, for instance, in the case of these images, you have a binary classification. So you say, yes, it's present, or no, it's present. And that's basically why we call that deep learning, because it's a deep network and based on neural network. And that's where we really saw the opportunity at Prodrive. We have image data, and deep learning is a very good candidate if you have image data to learn these relationships between, let's say, data and labels. So we started out, I think, a few years ago, really with our first pilot project with deep learning. And the use case here was we have cables. There's a product where you put cables in a certain connector, and we had to inspect actually if these were correct or not. We still do, for some products, a lot of manual inspections. People manually are looking into these products, looking at the cables, and in this case, checking if the order is correct and if they are inserted correctly, so deep enough. So it's not, let's say, if there's a piece of metal visible, then it's not okay. Back then, we were just starting with deep learning. So like, yeah, we can do it with computer vision, but it's hard, right? We can probably detect the colors, but the insertion, that's really hard. And this is also a setup that is it's a workstation. It's not enclosed. So there's light coming from all directions. There's people walking around. The lighting conditions are thus not very stable. We should try deep learning. And then we actually started with that. But then we needed the data set. So we needed somebody to actually collect all this data. And that's actually what we did. So we had somebody for a few days pull out the wire, take a picture, put it in the wrong way around, take a picture. Really somebody collecting a few thousand images, which took, I think, a few days. And then also labeling them. So this is pass, this is fail. And we used an architecture called FinNet. Maybe people, not sure if you're aware, there's also basically the architecture defines the ordering of these layers and these neurons. And I think ResNet is maybe some people
more popular. Yeah.
More popular, right? ResNet. We use EfficientNet, which is an evolution of that architecture. And it was really successful. So we found out that this model was capable of learning this relationship of these input images and giving them a pass or fail. So we had images of wires being correct, let's say the function class, and we had images of where they were in the wrong order or just pulled out or not pressed in deeply. And this model was capable of finding this relationship. And then we thought, okay, this is really powerful, right? We got to use this more because people in our factory can do this by themselves. They can take these pictures, they can label images. We don't need to be involved. This model can train it by itself. And then we thought, okay, we need to apply this much more, but there are some caveats, unfortunately, because it's not, you can just add more models and everything will keep on working. Right? So the big challenge here is you've trained your model, but how can you guarantee it will keep on working? There's no guarantee. You have trained on a certain input data set. And I have an example. At some point, they changed the color of a cable. So we had a black cable and it was white without informed pass. So we didn't read the model. We just kept on going. At some point, they got a lot of incorrect predictions, right? So the models, the cable's not present. People are like, yeah, but it is present. So what's going on? Why is it making a lot of mistakes? And they notified us like, it doesn't work. Can you fix it? We're doing it manually now and then we don't trust it anymore. And looked, yeah, but the cable is white. Yeah, but that's a change. You didn't know about that. That's how it goes, right? Yeah, then we had to retrain. That can retrain the model. We added new labels, new data, and it worked again. It's fine. The model can generalize to recognizing a cable being black and white, or white, let's say, black or white.
Yeah.
Okay, that's very nice. But I'm just mentioning now one example where we train one model. And each product can have maybe dozens of,
Multiple.
and we have thousands of products.
So this becomes unscalable all of a sudden.
Yeah. But so challenge there really is, okay, this is really nice, powerful technology, but how can we make it scalable? And again, in the beginning, we labeled even ourselves, right? As engineers, we labeled, not the people in our factory. So you can argue that's even more expensive than just letting people in the factory do the inspection themselves. So there's a transition period where it's more expensive, but at some point you should wait to scale. And so automating these inspections is really important also, because you have people doing it in the factory. They are very good at it. I'm really amazed by it that they can do this for hours and don't make any mistakes, because they don't make any mistakes. If I try myself for 15 minutes, I completely lose focus, cannot do it. So they're really good at it, but still they have some limit, right? They're humans, so they get fatigued, they make mistakes at some point. These are the product we ship to our customers. So we want to improve on that. And another thing that where automated inspections can help is it gives you more traceability, because we had no idea what was going wrong on our products on a detailed level. We had a high level idea on our presence defects. Sometimes we have alignment defects and all that kind of things, but we don't know exactly. So we need to track this somehow. And you can ask people if there's a defect to accurately enter it into a database. But yeah, that's a lot of extra work and they make mistakes. And so it's really hard to do. So basically, this automatic visual inspection is really there to improve quality and get more logging on your inspection service.
Right. So I'm assuming that people who are doing these inspections, so components are coming at a relatively high pace, they can visualize it, they say yes or no. But if there's a root cause of some miscalibration or something further back in the process, the people doing the inspections, they themselves don't look for patterns. They will not have the skill set to say, oh, there's a slow deviation happening. That must mean that something, maybe one of the engines on the conveyor belt is getting torn, or maybe a motor is not working, or there's some hair stuck in it or something. Those kind of things that I think are quite normal in production lines.
Mm-hmm.
They won't find it. So I guess this automation has got a hidden benefit that it enables you to find these patterns and then predict ahead of time when they would go and maybe fix it, right? Or even have a better understanding was the process itself, could it be a little bit better? And you can't blame the person who's doing on the inspection line saying, yeah, it's slowly but surely getting worse. I don't know. I'm just staring at this thing. I can see it.
We do have quite the experts at this process who have done this for multiple years, and they can spot stuff like this. And they actually probably know, I've seen this before. This means this group is actually deteriorating. Replace it. So at some point they do see these things, but for new products, they might not. And we only have a limited supply of these really good people. We also have the people who just started the Prodrive and are now had their training in visual inspection and the products. Again, we're growing really rapidly. So you're going to lag behind on that expertise at that point, right? You still need to make all these products. Yeah, that's basically the challenge.
But then just to maybe circle back to something you said, do I understand correctly that for every product you build, you have a separate model, or do you generalize one model for every product, or is it one model for every category of product? That must have been a fun discussion. Walk me through a bit of your thought process there.
Yeah, we started a few years ago with this one model, right, on this cable inspection. Actually, there are multiple of these cable connectors on the product. So for each of those connectors, we train a separate model. So there's already multiple models for one product, one end product. That's how we start. And that means if you have a new product, again, need to gather a lot of data for train a new model. It would be more ideal if we can reuse an existing model, because it has already been proven on, let's say, a product, although the data is different, but you might need less data to train it because the model already understands what you're trying to do. So let's say you have a connector where we check the presence, there is green. And now we have a new product where the connector looks exactly the same, but it's red. And I already had the example of the wires, right? Where they changed from white to black. In that sense, we only needed a few images, let's say maybe 10 or a few dozens that we added to the model to retrain. And then we already had good performance again. Start from zero, you need maybe hundreds or thousands of images, depending on how hard your machine learning application is for your problem.
Yeah.
We tried to find indeed that sweet spot. And for another product, we started with, let's say, I think 3 models for certain components on that product. And then we thought, okay, we have all these variants. They actually look the same. Could we just train one model that can do all of them? And that's what we did now. So for a certain product series, they're using the same model for different products. And the only thing that differs is sometimes one connector is different, or a position of connector is slightly shifted to another place. And that's basically how we can reuse models and also scale a bit, because it is really hard to manage them. But we already see, we started with, let's say, 10 models. I think now already a few years later, a few hundred models. Yeah, how can we keep on doing this? And especially because, as I mentioned, we now also still as engineers, we train these models. It's not the factory.
Mm.
That's where we're aiming at.
So there's a couple of things here that I need to dive into to understand. One of them is, so you keep saying models. So I'm assuming there's a lot of Python behind the scenes, right?
Yes.
So Python, there's a lot of programming that's going on. But you said you keep mentioning data and images and quality of images, and that's a driving thing. Is this the fact that the deep learning model itself is somewhat a commodity, and it's not which algorithm of deep learning you're using is the key here, but is the driving force, the quality of the images, which is so specific to you at Prodrive that actually your added value is being able to get these images in a good, clean, consistent way? Is that a true statement, or am I looking at this in a very naive way?
That's very true, because I think it has been proven quite a lot, also in research lately, that you can get, let's say, that 0.1 extra % by getting a better model. But yeah, just improving your data and being in control of your data distribution and weird outlier samples obviously can improve your performance way better, because the model doesn't have to deal with all these irregularities. And that's the main thing we also saw when we were developing this. Yeah, you can train your models, but that's not the main problem. We should gather our data in a really structured way to be able to train our models with good data. If you give the model bad data, it won't produce any good results and gives you bad performance.
So tell me a little bit about this process that you have. So I'm guessing you've learned quite a few lessons along the way. So this is the definition of going from idea into production. So getting machine learning or deep learning into production. It's not so easy, because I'm assuming you have time constraints, right? So it's not that you can take 10 seconds for every single product, right? So I'm assuming you've got a line and these things are going quickly. Can you maybe speak a bit about some of the constraints that you have, and then maybe how do you put a process in place?
Yes, I guess it depends really on the process. We have some places where the inspections are fully automated. So it really depends on the other processes around that, how quick you can do it. And in that case, we have a minute. So then there's not really a deadline. We also have places where people are, let's say that we call them semi-automated. So people are inspecting next to the automated inspection. That has to be at least as fast as them, otherwise they're waiting. And we had that, taking a time, come on, I need to do the next product. I cannot take a picture yet. It's still calculating stuff. So there we did have to find a solution. And maybe I should introduce the term MLOps.
Yeah.
That's, I think, a very important keyword here. If you look at DevOps, I think that's a term very well known. A lot of people, where you version your code, you have automated tests, you have automated deployment pipelines, you're versioning, and that's all very clear. People have been using that. It's a standard way of developing software, right?
Yeah.
Developing machine learning, that's a whole different story, because it's not only software. You also have these models, which I'm talking a lot about, but you also have the data, as I mentioned. These will have effects on how your entire system will perform. If you change the model, it'll work very well. If you change the data, let's say you change to a different camera or different camera setup, model might not work at all. If you change the software, clear, right? You update an API interface, the thing might break, or an incorrect data might arrive at your model. So you really have to keep everything in control. And you have the DevOps, which is about the software and the deployment, monitoring of your software. With MLOps, add basically 2 extra dimensions: that monitoring your data and monitoring your models. And we found, we really need to get this under control if we want to get this in a robust environment, because we're a professional electronics company. We have really robust, processes that need to be stable and robust. You cannot say, our model is not running or our model is slow. Sorry, we can't produce today. No, they have to work always and work reliably. So we need to implement this process. So we need to have a system to manage our data. We need to have a system to manage our models, with training the models and experiments. We need to have a system where if the model is safe, you need to deploy it on a stable environment. And then when that's all in place, very important, you need to monitor your models and your data. Because if you don't do that, you have no idea if your models are drifting, or is it the model that's drifting? Is it the data that's drifting? You just mentioned, indeed, let's say your belt is wearing and your products gets changing a bit over time. This is something you could pick up, but who picked it up, right? Is that a person? No, it should be a system that does it. So those are really in my opinion, the 4 key components: data management, model serving and deployment, and the monitoring part that you have to set up.
So you did this from the bottom up, right? So you started with a proof of concept and now you're expanding. So maybe can you tell me a little bit about the tools that you've built in each of those components? Can you talk a little bit about them?
Yeah, sure. So we are combination of these tools we're basically calling the Prodrive AI framework. And maybe a disclaimer already, maybe the word framework is not correct, because it should be a platform actually, because in the end, it should be an application that people in our factory can use with an interface ready to use. You don't need any other software to integrate. That's not what it is now. So let's say for now, it's still a framework. And then indeed consists of a lot of Python components in this currently. And I think there are maybe a lot of other motivations why you would not do that for certain components. But there's one main motivation is that our team consists mainly of machine learning engineers. They're proficient with Python library like TensorFlow, Keras, PyTorch. And we also have a lot of other software engineers at Prodrive, and they're working on a lot of other important projects that we also had to do with the people we have. I mentioned this other piece of software, which was a C#. Those people don't know about Python and machine learning. So then you really get these couple teams. And we really thought, okay, this is something we have to first build ourselves and prove to the company we need this, and we can show them the benefits. So maybe let's start indeed with the first part of the data management, where we need to manage all our data, collect our data. We made a specific data manager for our image data, and then maybe even more specific, not just image data by itself, but really on the automatic visual inspection. What that means, we also have a data model around it to specify which product are we inspecting, from which side. That's a product view. And on that product view, which parts, so regions of interest or ROIs in that product view do we inspect, and what do we want to inspect on that ROI? And that's something we call an inspection task. So is it a presence task? Is it an orientation task? Is it maybe damage or misalignment? Those are all the different types we specify. So we really made it explicit how we are going to, let's say, use our data that we collect over time. And did that on purpose to really say, it's not just big pile of data and we train a model. No, we also know what is in the data and what it means. We really made it explicit. In that sense, we needed something to support us in Python. We started to use Django now for quite some years. So basically with Django, we defined this data model around defining these inspection tasks and products and views and the regions of interest. And it does much more. It also stores all our predictions. It also keeps track of the models, but that's maybe not data management, but that's a separate part of it. But then you could argue, okay, but you collect this image data, but are you storing it in a database? No, we are storing that, let's say, in S3 compatible storage. And the only thing the database contains is the link to that storage. So basically you have a big table that links everything together, where you can say, okay, this sample is then an image has been captured at this point in time. So very important, this point in time, at this setup, maybe with these camera settings, for reproducibility, really important. Yeah. And it's this product, and we will execute these tasks on it. And basically that's how we set it up.
So I have limited understanding of computer vision, but it's not if you have one camera and then you put another camera that you get the same results, right? So cameras have very different properties. And when you take a picture, there's a lot of metadata, there's a lot of compression going on, but there's calibration, lens sizes. There's a lot of parameters associated with any image, and especially where you put it, right? So if it's a few millimeters to the left or to the right or the angle, that can have big differences, right? So I'm assuming that you try to be as specific as possible to reproduce these setups, and you have to store all of that. So I think naively people think, oh, you just take a picture, how hard can it be? But there's many more little real engineering problems associated with it. And that's why typically I think many companies say, look, I don't have the team, the power, the bandwidth to do it myself. I'll just outsource it. Company X, you come in, give me your cameras, you install it, your problem. And if I have a problem with it, I call you and I pay you X amount every year. This thing has to work.
And we didn't do that. Yeah. And really also maybe in the mentality of Prodrive, because we already had the competence to know about all these camera setups. We're not just an AI software company. No, we're an electronics company. And our main competences are mechanics, software, and electronics. So we know about camera systems, and we also built our own cameras, actually, not computer vision cameras, but really high-end electron microscope cameras. So it's a completely different regime. But we have a lot of experience with that and building automated setups as well, as I mentioned, for the manufacturing line. But it is actually how we started. We just took a picture and stored it on an enterprise. That's how we started with this first case. And it was a really long image name, because the image name contains, I think, the serial number of the product, the timestamp, maybe product number, maybe some extra parameters, but at some point, it doesn't work. We just need to store the image and store all the metadata somewhere else in the data.
So that's where Django came in, right? Cool. Okay, so you got a Django going system where you got a framework that stores pointers to where all the images are in an S3 compatible drive. So every new image, it gets categorized, logged, and I guess the vision is anybody should be able to do this. But at the moment, as you're building this platform, until you get to the platform itself, you're figuring out some of the details and you're doing it. Okay, cool. So please continue. So then what else is there to know about this?
Yeah, Django is just, let's say, object relationship management tool, right? has a very nice admin interface. But for us as developers, it's really nice to maintain our application, add new products, add new tasks. But you need a better user interface if people in the factory want to accept it. So in that sense, we're building other front-end things on top of that connect to Django to be able to define these tasks. But that's more, let's say, JavaScript. We're looking at Canva, which is a nice library where you can have a canvas and you can drag all kind of rectangles. We're looking into that to build a nice front end on top of that so people can actually define their own tasks. We do have a labeling tool, so an annotation tool where you get the image. You have all these regions. You can click a region and then say, this is password fill.
Because but self-built or board? Okay.
So we did compare a lot of tools, but for this specific case where we link to these tasks, our own data structure, we need to integrate so much that actually the work of just making a simple UI was actually less than the integration of integrating an existing tool.
Yeah.
So in that sense, we said, we're just going to integrate it. It is also really a simple tool where you can just click it and click password fill or say that's defect. And that's how we can collect labels, because we just used to do that with the folder 0, that's a pass, and a folder 1, and that's a fill. And that's how we did it on a network drive. But again, it's not really easy to use for people in the factory, all those kind of things. So then a nice annotation tool. We're building a new UI on top of that. That's React also to have a more nice feel for the user, really get the adoption going. Okay, but that's great when we have our data stored. We have it tracked. We know where it's been captured. And maybe good to point out why it is also relevant, where it was captured, how it was captured. We have sometimes, and will even more in the future, multiple setups where the same product is inspected. It might look different in different setups. We want to know if a certain setup does not perform well because, I don't know, somebody turned off the light or somebody moved it and it's now in a dark space and we don't have enough light to capture the image, that we can actually find this.
So it's like when you're building a spaceship, right? You build in redundancy left and center. Same thing goes to ensure quality of your production lines. Okay, nice. Yeah.
And the really key factor here is I call it data management system, right? Or a data management platform. You need to have the reproducibility, but actually what you're doing is you're basically versioning your data. So to say, you're adding traceability and versions to your data. Because how does it then relate to machine learning? Okay, now we have this nice data management framework. How can I train on it? So what we added on top of that, we define a thing called a data set. And what it actually is, it is a frozen in time capture of your samples, your region of interest on the samples. The sample is an image, region of interest on that image, and the label of that specific part of the image. It's just serialized. So it's a big serialized file, so to say, where we fix this information. And it also contains obviously the URL to the file. Yeah. In theory, if you have the right access, we don't have any fancy, let's say, data lake, binary storage where we can actually version that. We might do that at some point, but we don't need to because we don't directly interface with that. We already have our management here on top. It's just the storage. So in that sense, we cannot, somebody could just replace the image there. We cannot guarantee that, but nobody has rights on that. So that's for now fine. And then we have this data set. That I think is the critical point. Okay, now we have a nice baseline to start training our model. This data set. And then we can reproduce it because this is basically where we started on.
Nice.
And actually, maybe a fun fact, we're now, and let's say next Friday, we're going to have a workshop where people will use these data sets to train their own models because we have our own IT, build some tools that they can use around TensorFlow to make it a bit easier to stream these data sets and then train our models.
Nice. Okay. So now I see that the data part is a big part of what you're doing. So then tell me a little bit about the model. So I don't think we need to go into the details of all the variations and which models you're doing and not using. But so how do you actually maintain? And I guess the real question is, how often are you updating and changing, upgrading these models, right? Is this something that for every product, you do it once and it's static, or is it learning as it goes? Does it get uploaded and upgraded every 10 minutes? What does that look like?
Yeah, so automated retraining and or active learning, all those kind of things are very nice in applications where it's not a big problem if you sometimes make a mistake, like a prediction incorrect. Take an example of your phone to recognize faces, right? If it doesn't recognize your face sometimes, but in the next frame, it's fine again.
It's okay.
Then nobody notices, right? In our case, if we would make an incorrect prediction on a product, it means we might actually ship a broken product to a customer. And they won't be happy about it because it's really robust. We really want to offer robust production. And maybe that goes into a bigger machine that is some medical application or some semicon application that cannot
This gets expensive very quickly for you.
Yes, he has to come back, service, you have to explain, you have to back, sorry, no, we'll do it better. We had even cases where we didn't have manual inspections, where we had two people actually inspecting the same product because they believed that we could do it. So we had two separate people looking at the same product, really expensive. Yeah, you have to deal with that.
And the other way is if you build something that's working perfectly and you say it's not working perfectly, that's a bit of a waste.
Yeah. What we have to do here, and that's where it is. So the question is, how can you then use this data set to train, right? And do we then retrain often or not? I think in most cases, because we build our own camera setups, we have the conditions pretty well under control. So in that sense, we take image, and as long as people don't move the setup, then it's happened where they moved the setup without telling us, and then it was under a light. Everything was very overexposed, so we couldn't inspect anything anymore. Quickly found out because we have the monitoring for that, but that's for later. So in that sense, try to get a really nice representative data set to train a model. We validate it on a separate set. And if that's good enough, we can actually start to do a trial run in production. We actually let technicians in the factory also make defects themselves. And then we can spot them. Like the final qualification, if it passes that, then we accept the model and we replace it as the automated inspection instead of manual inspection. Right. Basically how we do it. And then if there's no reason to retrain it, we don't, because we also have a big quality department, and basically you have to write documentation for them to prove in okay, we have this data set that the model has never seen before, and this is how it performs. It's representative for production, and this is the performance. And they say, yeah, that's good enough. Accept it, or no, it's not good enough. But you need to improve a certain performance metric. Okay, then we have to retrain it and improve it. And that's basically how we do it. So we don't update automatically, because then we would have to go to the quality department again, right?
Every time.
Prove it every time. At some point, we could maybe do that if we have this in an automated way. There's one big problem. This means you also need to label some of the data in production. And the more models you have in production, the more you need to label. Obviously, you can do that sample-wise. So you just label, let's say, hard samples and those kind of things. So that's a very nice technique you could do, which we might do at some point. You also can do is look at the output score of your model. So if you have binary classification, it's a value between 0 and 1. If it's 1, it's very sure that it's a defect. If it's 0, it's a product that it's but at some point, it might deviate more to the 0.5, and then the model is not very certain. So we need to watch out. We need to retrain what's going on. We need to investigate. So that's basically how you can look at your model without labeling. Mm-hmm. It doesn't say everything. It might still say it's very certain that this is correct product while it's incorrect. We have seen that. And it can give you an example where basically at some point the camera was off, or the lighting was off, or the lens was a bit unfocused. We even had a point where there was a hand in front of the picture, and the model said, yes, this product is completely fine. Didn't even see the product. And that's the disadvantage if you train a model with binary classification. You only give it images of good and bad products. Don't give it images of a hand or black image or
the weird scenarios. Yeah.
Then it doesn't know what to do. So then it just chooses something. It basically almost random what will happen then. So you need something on top of that to deal with that. And maybe something I can also explain later. We do global anomaly detection, but maybe first go, okay, how do we actually train these models, right? Because that you have this data set. I mentioned we have this library. So basically we build our own Python library now internally for people in our team to use, but now we also want people outside our team to use it to see, hey, does it actually work? Does it make sense? So we have our own internal repository. We use Artifactory. That's binary storage, right? And they offer also a PyPy-like repository. So we use that internally to distribute our packages. And we're going to see how it's going to work out. So what does it do? It is basically just a wrapper around, as I mentioned, TensorFlow, Keras, that does some extra things on top. Because just training on the data directly, that is possible. But it's very likely that your model will then focus on, let's say, the tiny details in your data set. For instance, let's say your lighting is a tiny part on a piece of metal and that's always there in the right corner. And even worse, it could be that the shiny part is only there when it's okay and it's not there when it's incorrect. This means that your model will probably focus on the shiny part, indicating that the thing is okay or not, instead of actually the part being there or not. It's using the incorrect information in the data to make the labels, which means if we go to a different set where this reflection is not present, you don't know what it will do, right? It focuses on the part, but you don't know. So what we actually do, and it's called data augmentation. So when the images come in, we do things to it. So we basically add noise, we shift it a bit, rotate it a bit, all the probability. So we don't apply everything always, but depending on a certain probability, we apply that augmentation. So yeah, noise, rotation, shifts. We also change the hue. Even have one new application where we just remove a part of the image. So we just fill it in with black or some other noise, just to make sure that the model generalizes. It's quite an important thing to note. So that's what you try to achieve, right? Your model should generalize to recognize the presence of a component and not recognize a certain lighting condition or a certain exact color of a component. So that's not what the model should focus on. So with this augmentation, we try to help the model a bit to not focus on the details, but really focus on, say, the bigger task.
Right.
And basically, we build a pipeline. So the pipeline is streaming regions of interest. Then we have an augmentation pipeline that is then fed into a training pipeline of, let's say, TensorFlow or Keras. I didn't mention PyTorch. We do also have some new models that we want to implement. There's a really nice library called Anomalib. And basically, it contains all kind of PyTorch models that can do anomaly detection. So that is something we do also want to include. So basically, you train your model and then there's an MPOX going, right? And at some point, you see the performance. What is very important to do here when you're training, you also need a validation set. So good to mention, if you train a model training set, that's basically where your model looks over and tries to find out this relationship between input data and labels. And then you have a validation set that after each iteration, which is called an epoch when you're doing deep learning, it validates against this set. So it doesn't train on it, just sees, am I going in the right direction? Right. Why do you do that? If you keep training on a training set, you could say, you can do this indefinitely, right? It will keep better and better, keep getting better and better. It will, but it will basically overfit on your training data. So it will get really good on that one, but it doesn't generalize anymore. It will focus on tiny details. And with the validation data set, what you do, you try to see, when should I stop learning? When should I stop training this model? Because at some point it will get better, keep getting better and better on the training set. But for the validation, it will at some point become worse.
Getting worse. Yeah.
Then you okay, wait, now we're coming at a point where we might need to stop. You let it parameter called patience, so you can try it for a few more times, and then okay, if it doesn't improve, say okay, now we stop. This is the model how we're going to actually try to use it. And so then finally we have the testing set. This is really after all your training is done, we assume that it's correct, and we then validate the testing set and get the final performance metrics. And if that is all okay, then we can go to the next stage.
Okay, so let me see. So that's, I guess, the traditional way of having testing, validation, and training sets. You split it up, but you have different percentages. But I think you're doing this for data science. This is very clear. But if your end goal is to have a platform, you also want to be careful that you don't have the people on the assembly lines taking pictures of always the same thing, because that introduces also bias and it focuses on things. And there's an art in choosing data, right? And getting the right data. So people underestimate that. And actually, I think many networks which are out there, if you dig deeper enough, the way that things were labeled, you might actually say maybe labeling could have been done better in the first place, and people are none the wiser, right? Okay, so then you train it. So then what happens next? So now you've got all this data, you've got these models being trained. You've also got some code around this to do this. So how do you bring it all together, and how do you make sure that you catch things that don't break? So I'm assuming that no matter how much effort you put in, there's weird stuff that happens. How do you catch that?
In general, we tend also to use a test data set that has been captured in a completely different date. So we can already evaluate somehow if indeed the model does generalize, but still you're indeed a bit dependent on how you capture the data. And it always starts with the data. If your data is indeed just really simple, always kept in the same spot, you try to generalize that, obviously it will fail. So that is something you do have to watch out for. Although we do quite extreme augmentations, rotating, flipping images, complete hue imbalances. So they do completely different than the original. That helps a lot. But indeed, how you then store this model if you're done.
Yeah.
But then what do you do then? You want to do experiment tracking, actually. That's a very important thing. And we use MLflow, a nice Python tool, to track this. And MLflow, we use it for two main purposes. So one is to track the experiments during training. So you can basically see these performance graphs. I mentioned the performance on, let's say, the training set and the validation set. You have loss functions, so you can see how well your model is performing, but you can also look at recall and precision, other metrics, basically how much defects it's finding of all the defects and how much it's classifying correct as incorrect. Those are really important metrics that we're using. So you can track those. And then finally, when the model is done, we also store the artifact of the model, which is like filed with all the weights of that model. And basically that you can then use later in production to infer on new samples. With MLflow, it also allows you to compare between runs. So let's say, actually, I want to try a applying this augmentation a bit more, because I think we see that the model fails on these type of samples. I think we think, and that's also an important thing to note later, we think because we cannot look in the model. It's a black box model, right?
Yeah.
Explainability, a topic we can
Yeah.
talk about. But you can compare then these runs together. You can see how different parameters of your model and different augmentations influence the final model performance. And then when you're happy, you found the best combination of those parameters. You found your, let's say, your model that has won the race. You want to register it. That's the other part of our MLflow that we use. So we use the model registration functionality, and that's nothing other basically than adding a version to it. You see, this is my version 1.0 that we're going to use in production.
And I'm happy with it. And you tag it kind of thing.
Yes, we tag it, and you can basically see its entire lineage.
Yeah.
What is it trained on? So data set, what augmentation have been applied, what is the architecture that you use, where is it trained, on which piece of hardware, all those kind of things you can see. It can help you debug later to see how you could improve it. Because if you don't store it, you have no idea. And for a great example where you had somebody in our team who had trained a model very nicely in his own Jupyter notebook, and we didn't have a notebook. We had the data, and the data again wasn't the data set. It was just a folder somewhere and a few folders. So we didn't know if we used all of that. What was the validation training? The model didn't really work for a few months, and then it started to deviate. Yeah, we just had to start again. No idea. And we really want to avoid that, because you should be able to retrain an existing model. You need to know how it got to the point it got to, and all those things you need to work out. So that's really the important part. And you have a tagged version model that you can build up.
Everything you've told me so far up until now, there's been a lot of visual inspections, right? Is that the only thing that you're looking into? I have to believe that this goes beyond just simple visual inspections, or is that like for the future?
No, this is a very good question, because it is, let's say, the low-hanging fruit. If you use deep learning on image data, because these convolutional neural networks work very well on this type of thing. But there's a lot of other data in Prodrive, and especially in our factory, that we can still use. An example, we have a lot of time series data, and we have a lot of tabular data. I mentioned our own MES system, manufacturing execution system, that stores all the process data of all our products in during production. So you can think about things of a pick and place robot, to the volume of the benzene, to, the temperature in an oven when you're curing something. All those kind of things are stored. And that's a huge amount of data that's like a gold mine we can still use to improve our processes. Let's say for some processes that are already very stable, it might not be very cost effective, but we also have processes that, let's say when you're just starting them, you have no idea when things go wrong, why that is. There's still a lot of information in those type of data sources. And I, for instance, also supervise a lot of graduation projects, either from here in Eindhoven Fontis or from the university. And one project I supervised was around anomaly detection on time series data. So we have automated screwdrivers, and when they're done with their task, they return the profile of the torque and the rotations. And basically with that, you could already, just looking at that profile, argue if the action was correct or not, the screwing action. Balance in place, like it must meet a certain end torque. And then we say it's fine, but maybe in between it actually slipped a few times and we don't know. We only look at the end value. So there's a lot of things you can already get from that to see, hey, my process is not stable, I should improve. That's the interesting for new process and new products you're integrating are not stable yet. So basically this is again a machine learning model that doesn't take images. It takes this profile, has been trained on many profiles, and then says, hey, this profile is anomalous or not. That's interesting because it's no longer binary classification. You can see it as binary classification, but we only train it on good samples. Then it's up to the model, let's say with a certain threshold or certainty, to say, yeah, this profile you just given me actually deviates a lot. Maybe you should check it out. It's also a problem with the images that you now have to label both good and bad images. A really key to note here, how do we get the bad images? We need to break products, right? We need to create these bad images. Good images, you mount the camera above your setup, run a week of normal production with manual inspections, and you have an enormous amount of correct data. And that's really where we're going more towards. We want to get rid of these binary classification models, go to anomaly detection, and basically only classify the defect. So you get an anomaly, you say, yes, this is actually an anomaly, this is a present defect. And then you get another anomaly, oh, this is an alignment defect. And in that sense, we can integrate much faster because now we need to collect that data, we need to train models on both, we need to see if they're balanced, right? Ideally, as many samples as good samples, it's really hard to obtain. Yeah. So getting this anomaly detection, I mentioned anomaly before, this is really the future in my opinion, because you just train on good data and you get already all your deviating samples from that you get as an output. It could be good if you just have a small sample size, it could be a lot of false positives or false calls that this is a defect normally. But if you can retrain, right? And then you can say, we keep it as tight as possible. So only on these good samples, if it deviates only a slight bit, we already say, oh, it's not fine. Please often lie way farther away than your correct samples. So we did on the time series, really saw the benefit there. We had another assignment for somebody who did this on our binary data, also really had good results on classifying anomalies. So this is also the next step where we want to integrate these type of models in our framework.
But that's the classical thing of, so you hire like a data scientist who's maybe more mathematical minded and cares about the model and figures things out on his or her own. But then when you go to production, just like with software, the versioning is really important. The testing, there's a whole bunch of other things. And the MLOps part, the way you've articulated nicely, is you're adding versioning on multiple things. And if one of these things is unclear, inconsistent, you can't really conclude anything. And this only works if you can tie it all together nicely. And people underestimate the amount of knowledge, effort, tooling, and infrastructure needed to tie this all together. And the premise is, if you do tie it together, maybe V1 is not good, at least you can get it better. And then step by step, you can make it so that V2, V3, V4 will slowly but surely get better. And then you can build out something scalable, right?
Indeed. And yeah, I think that's a very good point you made about, let's say, you hire a data scientist who does this, and data scientists might be very good at creating models or going through the data. Obviously, they're very reliant on the data engineer, because the data engineer makes it possible for the data scientist to have any data at all and have good quality data. So basically, let's say our data management platform is there to take away the data engineer role to already make sure that this is correctly done. Then the data scientist could train a model. But then a really important role is the ML engineer. That's the role that is bridged between, let's say, the data science world, data models, and the software world. Versioning, testing, consistent deployments, monitoring, all those kind of things need to work together. So that's basically the thing we're trying to solve with our platform or framework. And then another thing nice to add here is that the framework now serves for parts still us as engineers. Let's say applying new inspections in production. Eventually, people in production should be able to do this themselves. So we have people who have no software knowledge, virtually no software knowledge, virtually no machine learning knowledge, and no idea about all these hyperparameters and all those kind of things. Those are the things we want to abstract away. So these are abstract things. We just want to say, hey, you can create your data sets, you can add your labels. Here we have, you have a presence task. We have this example model. We know it will work in 90% of the cases. Please use it. And if not, then we can jump in and help. But because we have so many similar products or slightly similar products, we see that there's a really easy way to scale this and that people without knowledge do this. And there's a term often coined democratizing AI. I think that's maybe a nice term to mention it, where everybody can use it. And then maybe I mentioned ChatGPT, everybody can use it, right? Need to sometimes know what they're using and how reliable it is. It may be good to note, indeed, I mentioned this explainability. If you train such a deep learning model, it's a black box. It might look like it's performing really well. There are a lot of examples where, for instance, you change this exact pixel, only that pixel, and it will completely say suddenly that a broken product is right. Yeah. So in our case, that's not very likely to happen because we have everything under control. We're on camera setup, so we don't think like these are called adversarial attacks. But then still, our quality department is sometimes hesitant. Yeah, you have this black box model. You cannot really explain to me why these decisions. And that's a very important thing to be able to do. Maybe good to mention, we are also in a European consortium called Explain, about explainable AI, where we work together with partners from the Netherlands, Germany, and Sweden to make this a bit more explainable, to open these black boxes. And some of these models, let's say if you have a decision tree, they might already be interpretable. In a deep learning network, it's so many model nodes and connections, it's really hard to do that. But there are ways of doing that. That's basically what we're investigating in that consortium. And you have to think of things like a heat map. So you do a prediction on an image and it tells you, yes, because of these parts, I am making this decision. And that helps you in multiple ways. It can help you to see, is the model actually trained correctly? Is it focusing on the correct details? And it can help people in the factory to see, oh yeah, no, you're right. Actually, that part indeed. Now I see that this component is indeed incorrect because I didn't see when I just looked at the image. But basically, you have different types of explainers. You have model-aware explainers, which really go into the black box, try to get the information out. And you have model-agnostic methods, where you change the input image a bit and then see how the model reacts to it. So you remove a part and then see what it does. And then if the model says, yeah, I don't Now this is a path that used to be a fail. Then you go, okay, this part in the image is really important. There are smart ways of doing it.
Because I think historically in complex systems, there's always this concept of traceability, right? So you have a
Yeah.
set of requirements. You need to prove that we said it would do this, and you go all the way from the words, the use case, to the code, to the implementation, to the diagrams, all the way. And if you have a nice link, then people say, okay, I have confidence in the process of how things are built. And the higher the confidence in that process, the higher the likelihood that things will not go wrong, right? So if you control everything well, and I think that is well known for specific industries, maybe more than maybe automotive, healthcare, there's safety standards. But then when you come to what you're describing on producing components and parts, it's not like there's a standard or a safety critical association which will look at this, but you're pulling away from these best practices to be able to explain things. And I think it's very good that you have an external third-party qualification team looking at this. But it's also like doctors, right? If you give doctors AI models and you say, hey, this AI is saying this and it goes against your experience, it prevents adoption. And the idea is you want to accept and accelerate adoption for the better, right? So having that explainability is super important. And I like the idea of having heat maps to explain it. And I think often people forget about that element when learning deep learning models. It's like, oh yeah, what about this explainability?
Yeah. It's really also a very active research topic because there's all kind of Python toolboxes and packages popping up. We had some people looking into it, and at some point in this consortium said, hey, look at this package. And I showed it up. I should have known this 2 months ago. I'm trying to evaluate these explainers, right? Because how do you evaluate how good they are? If a heat map slightly more in this area or in that area, multiple questions. Is the explainer wrong? Is the model wrong? Is the data wrong? You have no idea. So there's even more levels of complexity how to evaluate these explainers. I think that's very interesting to look at. And that definitely will also help adoption in the factory a bit further. Yeah.
So Thomas, you've explained things really clear. MLOps is complicated. I think you've articulated nicely, and it feels that you're the mastermind behind this. So I'm assuming that you're one of the principal people at Prodrive making this a reality. I'm sure you don't do it alone. But if people want to learn more, how should they contact you? And what is the right way? Are there any events or things like this? Are there opportunities for people to come and do tours?
One also where they can help themselves, obviously, visiting your nice By Data Eindhoven, where a lot of talks are about this topic as well. But people, if they want to contact me, it's always, I think, nice through LinkedIn, because I think that's an easy way to enter a discussion. And maybe for people to help themselves, if they want to learn more about MLOps, there's a really good site to get started, which has been created by a lot of people from industry. It's ml-ops.org. And it's a really nice place to see what kind of concepts there are. What do you need to consider, right? I mentioned quite a lot during this thing, like data models. Where do you need to look at? You have really nice architectural overviews on, let's say, functional blocks you need to think about and implement if you want this to make this a success. Monitoring your data, monitoring your models, automated pipelines, automated deployments, all those kind of things you need to have in place. I think that's a really good starting point. And maybe as Prodrive already said, we're a bit weird that we do a lot of things ourselves. Maybe also good to mention, we built our own MES system, so manufacturing execution system, which is definitely something most factories would buy, or it comes with the machine that you buy, right? The problem is we have so many machines that they all have their own interface and systems. We need to somehow harmonize this. And we started with that, I think, 10 years ago. Back then, there was definitely not a good system that could do this. So because we started quite early on that, we are now using it with, very successful. Let's say we have no paper trails in our factory. Everything is digitized. So people sometimes say, where are your clipboards with all your papers to track all your products? What paper, clipboard? No, here, look. Yeah, scan the product and see where it is, right? And track all this data. And the AI framework can also say, maybe you should buy this. And we definitely have considered that. So especially for some components in this framework, we could contacted third-party vendors to see, hey, could we use your software? And there's a couple of reasons why we did not do that. So one is that maybe now there is, so we should evaluate this. There wasn't at least not one big, let's say, AI framework that we could reuse straight out of the box. Maybe if there was one, we have a super vendor lock-in, right? We're tied to them, and we need to integrate, as I mentioned, to our camera system, to our MES system, all those other systems. Then it means we're really, handed over to them, and they have to basically serve us if they want to. And if they have other customers that pay more, then too bad, you have to wait a year. That's, I think, the main issue why we didn't go for a full platform. But we might go for, let's say, one of these components. If there's another component, we can pull it out and put in a paid component, let's say, right? Yeah. Really see the need for it. Other than that, we're mostly using open source components. And that also comes sometimes with its downsides. At some point, we have a gRPC interface between our components, and we wanted to use for some of the components in the latest version of Python, which is I think 3.11. We used 11.0 or 11.1, one of the first versions, and we found out some async was broken there. So we built fancy async calls in our gRPC code, and at some point, really weird stuff happened. Couldn't reproduce it. We could reproduce it, but we had no idea what was going on somewhere in the depths of Python. So we posted it on the gRPC GitHub, and it took some time for them to test it. Next, there's no people you pay to help you, right? It's open source. We also have to do something yourself. So put it there, they retested it and traced it actually to an async bug in the latest version of Python, which is now, I think, patched in the 3.11.3. So it's obviously a downside if you use open source, but in that sense, it does work well because it's so feature rich. And I think that the main challenge there is you need to have people who are competent in your company and experts that can actually use it, right? And apply it. So the main people we also really need now, we're very good machine learning engineers and data scientists, but we also need a lot of software engineers to help us build this platform. And for instance, Django, we did a lot of building ourselves because Django is just packaged and you have to define all the code around it yourself. But indeed, with TensorFlow, it already works standalone, right? And also with MLOps, you need to integrate it. Basically, we're building this integrated framework, and we need software people to help us integrate that and scale it. Maybe the thing I didn't even mention is that we deploy all these components on our local Kubernetes cluster. You can see a lot of people would actually just go to the cloud and deploy everything there. It's quite expensive. And then the problem for us is, I mentioned we have image data. They're quite big. So that means a lot of storage, a lot of costs of data that you don't actively always need. We have many different products. So we really chose to do it locally. And the advantage is, hey, we also build our own server board. So why not use that hardware to build our own cluster, put all our software on it, and then we manage that. And that's what we're doing now. I think that was also a challenge to get that set up. For IT, it was also new. Everybody uses Microsoft and Windows. Locally, we do have Azure in the cloud, but we didn't have any Kubernetes experience. We really need this to scale because we have this party that could help us to deploy our model, to serve them as a web service. And they basically, it was a super, super nice package. The problem is we had to pay per model. And I mentioned that this will work, right? If you have a big company, let's say a bank, that one generic model that does like how much you can loan, or how much money you can loan, that's fine. You can pay a lot of money for that because you get a lot of money in return. We have also some products that we, maybe only make a few thousand per year, but we do deploy it on their software and we pay for that. That's basically for some products, even the cost of deploying those models might be more expensive than selling the products, right? So in that sense, that didn't work for us. There was also some conflicting scaling models that don't work for us. So that's another reason why we also deployed that locally. People, we need a lot. If we have people with Kubernetes experience together with Python, those we can definitely use, yes.
So I think maybe a key takeaway is just because you don't know of a company, it could be that it's doing B2B business, it's not mainstream. It doesn't mean by any shape or form that there's not a lot of cool opportunity for any and everyone who is technically minded. And you've articulated nicely that your whole MLOps workflow is evolving. You haven't finished everything. It's still a lot of work has been done, but you definitely need more help to keep building it out. Prodrive Technologies sounds like a cool company for people to take a look on if they're looking for career changes and make a real impact.
This is a great place to end this episode. I hope you found it interesting and it triggered your curiosity in some shape or form. At least enough to have a conversation with some friends and family about some cool, interesting insight of how MATLAB, Python, or Julia are actually used in the real world. If they do find it interesting, don't forget to tell them to subscribe to this podcast